We will study today a circuit with a diode. So I'm going to draw again as we used to do. I'm going to start drawing some a circuit here. You can also at the same time draw along with myself. Okay, so let's get started. On this side, for example, we have down here just a simple EMF, the ground. So this node is, I'm going to show here the ground sign like this. This potential is 0 volts. If we want to have a potential for this EMF, for example, we have a certain potential given here. So let's assume that this would be 12 volts. On this side, on the top here, I'm gonna draw one resistor. So let's write this as a 2.2 kilo ohms value. And over here, I will put a diode. We have a diode here. And just remember the direction of the diode. The electric current is passing through you. You followed us this direction here, this triangle. So the head of the triangle gives us the direction. And let's finish with another resistance here. And we're going to close with our circuit switch and the node down here. We have an EMF of 12 volts, 2.2 kilo ohms on the top here. And let's say this one would be 1.7 kilo ohms. 1.7 kilo ohms. Let's start first of all to draw the electric current, a red color for that. So this will go this way. Since the positive is here on the longer plate, the shorter plate is negative. Conventional current out of the positive, so we can draw here. Let me label it as I sub naught, so the initial or the principal current. This is passing through the resistor 2.2 kilo ohms, so creating a potential drop from those two nodes. So let's call this node A. This one is node B. So we have a drop of potential here. Now it has to pass through the diode because the direction of the diode is left to right. So the current passes through down here. Again, I sub naught, the principal current, through 1.5 kilo ohms and going back to the power. Now, again, all of these are, we suppose that we close this switch here on. So what we can say is that in this direction, about the diode is on. So the diode is letting the current passing through. The sign is in the right direction. So this is the positive, this is the negative. So the current is passing through this direction. So we have the positive goes through. Now here's the characteristics of the diode. For now, again, we are just focusing on two things. We can have a silicon diode. So if you have a silicon diode, I'm going to write it as an SI. A silicon diode is creating a drop of 0.7 volts. So there is a drop here. There is a drop of 0.7 volts here. Now, in some cases, we can have also a germanium. So if you have a germanium, the drop is just a 0.3 volts. So what does it mean? Let's specify, for example, that in our case, we have a silicon. This is a silicon diode. So we are expecting a drop of 0.7 volts. Now, if we do an analysis of this circuit, so we have the node A, we have a node B, we have a node C here with a small drop, and then we have the ground. So I'm going to use all the time G for the ground. So doing a simple analysis, the current is going from the positive EMF, passing through the resistor, 2.2 kilo ohm. We have a drop here, and then passing through the diode. So through the diode, we have a drop. Since this is a silicon, we have a drop of 0.7 volt. And from this part, passing through 1.7 kilo ohms, there is a drop also to C to the G ground. Then going back to the source of power, the electromotive force is 12 volt. So generally, when we study a circuit like this, in the last section, we'll be talking about electric power, but for now, we're going to use Ohm's law. So what are the different unknowns in this case? So we can talk about, since the current is the same, so whatever is our calculation, I is the same throughout the circuit when you make a loop. Now, we can have also to calculate VAB, the potential drop above the resistor, 2.2. We can calculate also the VCG, the potential drop over the resistor, 1.7 kilo ohms. So as I said, for now, we are not talking about powers. We go one step at a time, little by little. Which one can we solve first? We can solve for what we have here in the front here. We can solve for the electric current. In other words, if we consider the equivalent from point A to point G, we have in series 2.2 kilo ohms. 2.2 kilo ohms. We have to add also the 1.7 kilo ohms, 1.7 kilo ohms. So these are our total resistance. These are our total resistance. Are equivalent, if you will, are equivalent. Now the last thing to do is just to remember that the potential drop is affected by the diode. So instead of 12 volts, we have to subtract the drop due to the diode. So that would be minus, since this is a silicon, 0.7. So that will give us 11.3 volts. Apply Ohm's law. Now, one thing that we need to memorize a little bit is that, as I said before, we have always to do the conversion for our units to go to the units, ohms, amps. But generally, in some cases, most of the cases, we have a high resistance, like a kilo ohms. So that will, if you are dealing with kilo ohms, that will allow us to not to do any changes if you use a milliamperes for our current. So whether you use the same units, ohms and amps, or if you use a kilo and the milliamps, then that won't change anything. You multiply by 1,000, then you divide by thousands. So our principal current in this case is voltage, which is 11.3 volts, divided by total resistor, which is the equivalent. So that would be 3.9 kilo ohms. And when you do the calculation, you're going to have a value that will be expressed in milliamperes. And that is 2.9 milliamps. So that is the current passing through. Now, if we calculate the drop in potential VAB, we apply Ohm's law. So you multiply I0, which is the current passing through the circuit, no change. You multiply it by the resistor, so the resistor is 2.2 kilo ohms, and that will give us, let's keep again one decimal places, 6.4 volts. And to figure out the VCG, we do the same calculations. So we're going to do the same calculation, and that will give us 2.9. That is the current, the electric current passing through, multiplied by 1.7, which is the resistor value, 1.7. And that will give us 9 times 1.7. That gives us 4.9 volt. And from here, obviously, if you add up these two, 6.4 and 4.9 volt, then you get the total voltage we calculated before, 11.3 volts. So just review the calculation, review the method again. Important part we have seen here. If you have a diode, if the diode is a silicon, you have a drop of 0.7 volt. If it was a germanium, the drop would be 0.3 volt.